Okay, so we're back today, and we're going to keep progressing with our ability to design in steel. So last week we talked about steel columns, and that was building on what we had done 2 weeks before that when we looked at axial stress and strain. In between those two lectures, we looked at bending stress and strain. So now we're going to take that bending stress and strain and apply it to steel. The reason I like to do the bending one second is because the column one is a little bit easier to try to get your head around this buckling phenomenon. Because it shows up again in bending, but it's a little bit different. It takes on a slightly different visual look because buckling is all about compression, and a beam in bending has one side in compression and one side in tension. You can see the side in compression is trying to buckle. And so we're going to have to build that in to whatever our steel equation is. Now before I go a little bit further, I just want to reach out to you guys. I gotta say you guys are incredible and awesome. You guys, a bunch of you sent me personal messages that I just think were above and beyond and incredibly amazing and very, very much appreciated. I can't imagine how hard it is for you guys these past 2 terms trying to learn in this environment. And the fact that you've been so understanding of me trying to teach in this environment just makes me want to do better for you guys. So again, if there's anything that can be done to make the course better that you think could have an improvement on how you guys are taking in the information, I'm happy to apply it. But I got to hear it early enough that I can try to implement it for you guys. Your understanding and appreciation of, one of the very small elements of diversity and equality in this industry, of basically being a female in the industry, was also really appreciated, because it's half of you that are going to face the same thing. And I can't remember the exact statistics, but I think it might even be a higher female to male ratio that graduates. But that means half of you are going to be making decisions in your lifetime about developing families. Now, these same choices around developing a family can impact you whether you're in a male-female relationship, a queer relationship, any relationship, whether what's perceived as traditional, which I hate that word, or some of the new norms that we're coming across. At a certain point, when you make that choice to develop a family, there are new hurdles thrown up in front of you. And, part of it, I'm kind of going on a tangent here. I just, they do encourage us to talk about these issues, but it's hard to really apply into the structural engineering, or the structural curriculum, because it's less about choice and more about answers. So I just wanted to take a quick moment and tell you about some of my experiences. And again, this is off the cuff. I haven't planned this at all. But, at a certain point, right when your career is really kind of starting to move forward, is exactly when you usually feel comfortable enough to make the decision to possibly build a family. And at that point, you are definitely losing valuable experience time. So you're definitely behind on experience. That's the nature of it. And then there's perception sometimes that you're not committed or a part of the design community that you're within. So you see a lot of females in the industry, or the people in the relationship who are taking predominant child-rearing responsibility, have to make decisions. If they want to advance in their career, they usually end up starting their own firm. That's not the reason I left Blackwell. There were other reasons within there for why I left Blackwell, one of them being it was my partner. But most people end up starting their own firm. But that comes with a whole new set of hurdles and difficulties. So when I started my own firm, project life cycles in our industry are several years. So if I said no to a project before I found out I was pregnant, because I didn't want to have to be working when I had a baby, I wouldn't have been able to accept any projects. So that means that you don't get mat leave. And it's not about being able to take the monetary hit. It is about being able to have a project over years worth of work. I'm working on projects right now in construction that I started working on before I was pregnant with my second child. So if I had not taken those projects, I wouldn't have had years worth of work that I'm working on right now. So, you know, those are things that make being a parent in the industry very difficult. I worked directly through. I took 0 mat leave. On the day Malcolm was born, I had a hard deadline, and my C-section was scheduled at 11 o'clock. I got up at 4 a.m. and worked for a few hours to be able to submit my permit set to my team so that they could submit for their project. So, you know, these are all things that make it more difficult, and having the entire team understanding and sharing those responsibilities can make great strides in how we change perception about how this needs to be done. So that's it. And rant isn't the right word. Thoughts on some of this, or preparation on how you want to handle it. Just because it's a really interesting spot we're in the industry now. The communication, people are ready to listen to these things, and I just think you guys are in this great position to go out into the world, not demanding, but expressing these things on a universal platform to all the employers. Like, we will not stand for this inequality, and it has to be the whole team, whether you're the one giving birth to the child or not. This has to be a collective of presenting this idea that we need to all be treated the same and have the same abilities to make advancements. Okay, so let's move on. Let's talk about the engineering now, which is really what you guys want to hear from me. I know, that's what you guys find super exciting, is all the math. So we're going to do a quick recap of what those bending stress and strain relationships look like that we talked about 2 weeks ago. And then we're going to take that. I already introduced steel to you last week. So we're going to move right into the beam equation so that we have time to do several examples, because they take a long time. They're long, complicated math examples. So I want to be able to give you guys the time to do a few examples. My goal is that whether it's the long, complicated equation or making use of the tables, at the end of this lecture, you're going to have 5 examples, and then within the assignment, you have several examples as well to prepare yourself for the exam. Obviously, the entire exam isn't going to be one big steel equation, but it's nice to be able to work through the process several times. And how you make use of these equations changes depending on different criteria. So it's important that we look at one equation or one example a few different ways so that you can take as much from it as possible. I didn't make my mouse the nice big gigantic mouse setting for you guys. So let me adjust my mouse here. All right. It didn't do it. There it is. It just had a really slow delay, which is pretty much how my computer seems to be working lately. So we're going to recap with bending stress and strain that we looked at 2 weeks ago. Now you guys remember that all of our kind of forces we're looking at tend to have this force that we're looking for or talking about equaling the maximum stress that we can see in our element and a shape property. And for axial loads, that shape property was area. And then when we need to, we add in our reduction factor so that we can be talking about our reduced capacity. So we looked at, with steel, or an element that has a plastic zone, 2 different versions of the same equation, but they were really, really, really close to each other. S is when we use the shape property for elastic bending, meaning we stayed in that fully, totally on that straight line, and the second our extreme fibers started to hit that maximum yield stress that we cared about, we stopped allowing any force to go into our object. If we talked about plastic stresses, we used a different shape property that was very similar to S, but it just said, let's allow our yielding to go all the way down to the neutral axis. Beyond that, and we kind of have a runaway train, we're going to have a lot of deformation, but we're going to allow just the tiniest amount of permanent deformation coming right down to the neutral axis. So what we're talking about is if we're bending it like this, if we're talking about elastic bending, that maximum stress would only happen here and here. And if we're talking about plastic bending, we let that maximum stress in compression come all the way down to here, and in tension come all the way up to here, so that we're coming up to the limit right here. We also looked at what those shape properties would be if we were talking about a rectangle, knowing that it's not always a rectangle, that this S value and Z value have a different equation here if they're a different shape. But if they are a shape like this, a rectangle, S is B, or our width, times D squared, D being our depth, divided by 6. And if it's plastic stress or plastic bending that we're talking about, it's the exact same process, except it's divided by 4 instead of 6. So we can take a little bit more force into that beam, or we'll allow a little bit more force to be carried by the element. We didn't do the big, long, complicated derivation of it, but we did look at strain for bending. And strain for bending, we saw that depending on the load distribution, and remember those are those fancy beam tables that could have a point load in the middle, or a uniformly distributed line load, or a triangular load, or some varying load, they gave us different actual deflection calculations that would be dependent on the load and the length. But look, they also had in here a shape property. And again, we didn't derive it, but we saw that for a rectangle, there is a shape property that is BD cubed divided by 12, or B times D cubed divided by 12. So for all of these things, we can take a look at what we know and what we don't know and start to try to fill in those blanks. So we could stop right here if that was the end of the problem, but you've heard me talk about a problem with bending, and it is the same problem we had in columns, which saw all axial load, and if it was a compressive axial load, our element tried to buckle. Bending is a little bit weirder because we know that one side of it goes into tension and one side of it goes into compression. Tension doesn't have buckling. Compression does have buckling if it's slender enough. So for an element in bending, our compression zone tries to buckle. So you can see my bottom doesn't buckle, but my top does. And as soon as it buckles, it bends out to one side and the whole thing tries to twist. So we end up, rather than just calling it buckling, we call it lateral torsional buckling because it moves sideways or laterally and then it causes it to twist. So lateral torsional buckling is something we need to add into this. There's one other tiny weird complication that is in no way something you're going to have to do any math for whatsoever. Up until now, you've probably been like, why is she talking about plastic and elastic bending and how do we know which one to use? If it's wood or concrete, the answer is easy. You can only have elastic bending. Concrete with reinforcing can be a little bit more complicated because we do allow the steel to yield. So that becomes a much more complicated problem that we'll talk about in several classes. Wood is brittle. There is no plastic zone. So the only thing we can use for wood is the elastic bending equation. steel, though, if we know our product really well, we will sometimes allow a plastic bending down to the neutral axes. Now, do you remember in the very first lecture and in the very first lecture of Structures 1, I talked about local buckling. Now, local buckling is different than overall buckling, like our lateral torsional buckling or our compressive buckling. Lateral torsional buckling is, I'm trying to, no, that's all too rigid. So lateral torsional buckling is when a local element within your overall object can buckle. So basically maybe one element within it is slender. So if you could imagine we had an element within our object do this. Let me draw, hopefully sometimes my screen kind of stops when I do this. What we're saying for this is that one of these local elements might buckle. So what they're showing here with this is they're saying that this flange right here could buckle. So not the entire object buckling or lateral torsional buckling, but just an element within it. Now, the way we handle that is we classify it. There's a bunch of math that can be done to back it up, but it's all been done for the different elements we know. If local buckling is really hard to achieve, we say, oh great, we'll let the plastic limit be what we design to. If we have a problem with local buckling that might happen in the plastic range, we limit our design to the elastic limit. So our steel elements in our book are almost all class 1 or class 2, but there might be a little asterisk beside it that says it's a class 3 element. If it's a class 3 element, we have to use the elastic limit, which means we use the S value. But most of the time, it's going to be a class 1 or a class 2, which means we allow ourselves to use the plastic limit, which means we use Z. If it's class 4, we care about local buckling even in the elastic range, but that's way beyond the scope of this course. There are ways you can handle it by looking at the ratio of stress usage, and I've done that for plate design elements. The canopy at Sisters of St. Joseph, for example, we were worried about local buckling because we had very thin plate steel where we could have had edges actually start to buckle on us. So we had to look at that as a separate design element. So for you guys, what you care about, is it class 1 or 2, or is it class 3? You're not going to have anything in class 4. And I can't remember if I give you guys anything on class 3 versus class 1 or 2, but I would be very explicit if I did. You would think I would remember, considering I just made all of these things recently, but I honestly forget. But I can guarantee you that, because I change things a little bit each year, and I can't remember what I chose to do for you guys this year, but if I do talk about something being class 3, you know I'm telling you that that means you use S instead of Z. So let's start to take these equations that we already knew and just formalize them a little bit. So just to try to get our head around it, just so that it's not just M, let's remind ourselves that M, if we want to say it's elastic or that we're using S, we'll remind ourselves with it by putting a little Y here. And if we're talking about plastic, we'll put a little P here for ourselves. So that just means that we're using our maximum stress times S, and if there's a little P here, it's our maximum stress times Z. There's no reduction factor applied yet. Now, remember that stress and Fy are the same thing. So let's just rewrite that stress as Fy, or our yield stress. We could have stresses lower than that, but if it's less than that, great, everything works. We don't care. What we care about is that limiting stress we want this thing to see, or Fy, which is our yield stress. Remember, it's the same thing we used in our column designs last week. And because we want to worry about our reduced capacity being greater than our factored loads, let's throw in our reduction factor now. So, for elastic bending, our moment capacity, or our reduced moment capacity, is going to be our reduction factor times the maximum stress we want to see, Fy, times our shape property, S. For plastic, it's the exact same thing, except it's our shape property, Z. This is all about strength. This does not talk about buckling at all. Now, strength, we are bending about this axis. We're bending like this. It's the same thing as if I was curling my fingers in these directions. Well, this is like saying I'm curling my fingers about this axis right here, which is my x-axis in those drawings that you see on the steel shape tables, or those property tables of our different steel elements. So S and Z, if we're bending something in the strong direction, is about the x-axis. So our strength is usually about the x-axis. Look what way it's trying to buckle. It's trying to pop that way, which looks similar to it trying to bend in that direction, or like that. That means our deflection problem, or our lateral torsional buckling problem, is going to be in the Z, or in the y-axis, about our y-axis there. So, that was all about strength. Let's talk about what moment it tries to buckle. At a certain point, for different lengths, our element is going to try to buckle. Again, this is just like our compressive equation. Lots of very smart professors and research people have developed this very, very complicated equation that, to be honest, isn't that complicated if you break it down. They've spent lots of time and lots of effort developing it, but most of these things involve properties of our shape that we can look up. So MU, think of it like our critical buckling length that we had for our columns. So it's the ultimate. So you could say critical, or you could say ultimate. So MU is the bending moment which results in lateral buckling of the compression flange. U stands for ultimate. But again, I find it somewhat annoying because when we're talking about columns, they call it the critical buckling. When we're talking about bending, they call it the ultimate buckling, or the ultimate lateral buckling. So they're talking about essentially the same thing here. Now, this W2, you're going to use it as 1. It is 1 if the moment is at the middle is greater than at the ends. Well, we know that when we're doing simply supported things, we have no moment at the ends, and the moment is all at the middle, or the peak is somewhere in the middle. So that means we would get to use 1. It would not be 1 if we were moment connecting the ends. It's kind of like our KL factor, or that K factor that we applied to our length. It's building in some how we change the shape within this. Pi is easy. L is the laterally unsupported length of the compression flange. This is critical. It does not necessarily mean the overall length. When I hold this beam up and I bend it, it is unbraced all along the top of this. John David, can you do me a favor? I need your finger. I need your finger for just a moment. Hold your finger just right here, just the lightest amount. Well, let's turn it a little bit for the fine folks at home. Look at this. Look at how much more I can bend this all of a sudden. Dave, how much force did it feel like was on the tip of your finger?
Oh, 4 ounces. About as much as a quarter-pounder hamburger sitting on the tip of my finger.
Not much is the answer I was looking for. Thank you. You may be seated.
My
Not much.
Highly calibrated.
Not much was the answer I was looking for. But in that example, the unbraced length was half of the length of this beam. If, actually, you know what, Dave? I need you again. Put a finger right here and a finger right here. I try to bend it now. It's buckling the other way. It would need to be held on this side too. But the unbraced length is now a third of the beam. So the unbraced length is a very important part, and it's the compression flange. If I reversed the bending on this and Dave kept holding up here, it wouldn't apply because this is the one in compression now. For you guys, we're always going to be looking at bending in this direction so that this is the compression flange. And you can look at the drawings or think about how that top chord is connected to the rest of the building to think about what the unsupported length is. If the deck is attached directly to the top of the beam, our unsupported length of the compression flange is practically 0. Because what they do, for the Structures 1 people yesterday, I actually made deck. Sad deck, but deck. It helped them understand that that was the direction of bending, or the strength, and this is not. Anyway, if we have a beam and the deck is connected directly to it, they often connect the deck every couple flutes. So the unbraced length is very, very, very short. It, like Dave said, it does not take much load to resist that buckling. In fact, it tends to be about between 2 and 20%. 2% is what we'll often use if we're bracing something at the halfway point. So it doesn't take much load to stop that thing from buckling. So if we're connecting it to a deck, we say that the deck stops that top flange from buckling. So if you have decks sitting and connected directly to your beam, your unsupported length of the compression flange can essentially be 0, which you can imagine you plug 0 into all of this, you do not have, or your critical buckling length goes through the roof. It's basically you do not have a lateral buckling moment that you have, critical lateral buckling moment that you have to worry about, because it's just braced. It becomes all about strength. E, modulus of elasticity. You guys know that, 200,000 MPa for steel. IY, the moment of inertia of the beam in the direction opposite to the applied load. We're applying load in this direction, so our SY is about our x-axis, and that means our weak axis is in this direction, or IY. So that's why when we're doing this calculation for a typical beam where we're bending it in this direction, we're going to be using SX or ZX for the bending part of it, or the strength part of it, and IY for the basically the weak axis or the lateral buckling moment. When we talk about stiffness or our deflection of our beam, we're talking about how much it moves right here. So that is, again, about our x-axis. So we are, for most of these problems, going to need SX or ZX, and we're going to need IY in our moment equation, but we're also going to need IX for solving our deflection problem. So we're going to need all of these bits of information. And I find that's one of the biggest problems people make, is when to use IX and when to use IY. So if we're talking about a normal beam and the way it typically bends, which is all I'm going to show you guys, You're going to need IY in your moment equations, and you're going to need IX in your deflection equations. G. G is the shearing modulus of elasticity, which I talked to you guys about last week. It's something we haven't calculated, but there is a relationship between G and E, and it's all about that weird bulging phenomena in our Poisson's ratio, which is all way beyond this course. All right, you guys are going to hate me with these two numbers. J and CW, they're more shape properties, but they're shape properties that help us. We could technically ignore this whole part if we wanted to, but it allows us to take a few other things into consideration. Some of it is about the ability to warp, and some of it is about the polar moment of inertia. Way beyond what you guys need to know, just know that they help us out. They make our lateral buckling moment, our critical lateral buckling moment, slightly better. So we don't have to worry about it quite as much. It helps improve the performance of our beam. These are big, ridiculous numbers that are going to be the bane of your existence when you plug them into your calculator. Do not forget at the top of your charts to look up what the times 10 to the blah, blah, blah is, because you're going to need that information. If you lose those base 10 placeholders, you're going to mess up your equations, because you do have to do it. You have to do the math at least a couple times. I try to make it as painless as possible, and I'm going to go through a few of them step by step with you. But again, these are just two more shape properties that you get to look up from the steel tables. I should have open, well, we'll be looking at them when we do some examples, when we go through the full worked out problems. So I'll show you those in detail when we pull them up. So that means this is what we're looking for. For you guys, this value is 1. Pi we know. L is the unbraced length, or LU sometimes we might call it. And for what we're going to do, it's either going to be connected to the deck and be almost 0. Maybe we have joists sitting on top of our beam, so it's not connected directly to the deck. We have a little bit of a gap between the deck. So for those ones, the unbraced length is the distance between the joists. Or maybe there's nothing connected to the top of it, and it's unbraced for its whole length. I will be very clear in the descriptions or in showing you how it's built or showing you drawings that how it's going to be laterally braced at the top. E, we know. IY, we know is a shape property. G, we know. J, we know is a shape property. And CW is another shape property. So this big, nasty, scary formula actually isn't that bad because it's mostly shape properties and things we know. The hardest part is not messing up when we plug it into our calculator. So this is all about weak axis stiffness. Look at this. There is nothing about Fy in this equation. The last equation had nothing to do with stiffness in its weak axes or its strong axes. It was just about strength. And this is just about our stiffness in our weak axes. All right. The way they work this equation is they get you to look at what is the MR if it is governed by strength? What is the MR if it's governed by weak axis stiffness? And then what is the MR if it's somewhere in the middle? In the column question, they put that all together, but they did put an upper bound on it. What they do with the beam version of it is they break it into 3 separate checks, and you have to figure out which check is appropriate. You have to look at them all and then figure out which one governs your design. So, if our buckling length, critical buckling moment, is greater than 2/3 of our yielding moment, then this is our equation. Otherwise, we have two different limits on this. So basically, we're saying that if it's, because see, we have this part right here, so we have a reduction factor in all of these. If this value is less than this, we would be governed, well, we're going to go through it step by step. We have our plastic moment, meaning it's just governed by strength. We have our critical moment, which means it's just governed by weak axis stiffness. And then this right in here is that zone in between. So we have to check all of these things and see which one governs. And we'll go through this step by step in just a minute. Look at this, 1 minus, basically a ratio of our plastic moment and our critical moment. This looks just like in our column equation where we had 1 minus a bunch of lambda stuff. But lambda was really talking about this ratio between our plastic compressive force and, we were using elastic, but our elastic compressive force and our critical compressive force. So it's the same general principle when we're talking about moment and we're talking about our critical buckling or the buckling of our top compression flange. So the best way to show you this is to break it out in the 3 steps. So you can see that if mu is less than this, we get to use this equation, but it has to be less than this. If mu is less than 2/3 of mp, we have to use this, meaning that the critical buckling moment governs, and somewhere in between this governs, unless it's quite short, and then just strength is going to govern. Remember, short does not mean the overall length is short. We're talking about LU, or that unbraced length is what we're talking about. If it is a class 3 section, everything is the exact same, except everywhere we had MP, replace it with MY, which really means that we use S instead of Z. So that's the only difference between the plastic and the elastic versions of this equation. And we don't even have to figure out which one it is. We just have to look at the table and see if it tells us if it's a class 1 or 2 or a class 3. And basically they're all class 1 or 2 unless there's an asterisk telling you that it's class 3. So if it's class 3, you'd want to use S to figure out MY instead of Z to figure out MP. Here is the equation, or here's the graph of that equation. Basically, the reduction factor times MP, which meant that strength governed, is this part right here. And we can see here that this happens when the unbraced length is very short. If our critical moment was less than 2/3 of this value, well, we saw that it was our reduction factor times mu, meaning this part all right here where our MR is equal directly to our reduced mu. So that's all of this zone. And then that middle portion of the equation, or this portion of the equation, is from right here to right here. So short unbraced length, reduction factor times my. Really, 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 really long unbraced length, reduction factor times our critical buckling moment. If it's somewhere in between those two things, it is a combination of those two things, and it changes its proportion accordingly. So let's go through, oh, no, there's one more thing we're going to talk about. We're going to talk about shear. Now, I'm going to tell you that in steel, shear doesn't often govern. It is much more critical when we talk about wood and concrete. That is not always the case in steel. We can have situations where shear is very critical. But for the most part, shear is not going to govern any of the designs we're going to do in this class. Most of the situations we look at, the load for shear ends up being split something close to equal towards the two ends. If we have a beam with, so if this is our beam, if our load is in the middle here, half is going to go over here and half is going to go over here. Shear might govern if we had a point load all the way over at one end. So all of the load is happening right here. And that slip of this element being connected to this column could end up being critical. I'm not going to give you any problems where they're critical, where it is critical, but we're still going to track and check it because we're going to see when we start looking at wood and concrete that it becomes a bit more important to make that check. So, we're not going to spend a lot of time looking at shear because it's a relatively simple calculation. Here is the stress profile of steel, of a steel I-beam. So look it up here. We have all of this area and very little stress happening in it. Most of the stress seems to be happening along this portion of our element right here. Look, our stress is peaked right around here. Remember that whole weird thing where stress can kind of sometimes move around a little bit? Well, what they've done is they've said, all right, we're going to let it go up to here, but we're going to limit what the maximum stress we can see here as being 2/3 of this maximum stress. So here's the max. We're going to say, let's limit it to be right here. I'm going to take this right here, which is pretty close to the average, and we're going to say the maximum stress we want this thing to see is going to be 2/3 of the maximum stress we know steel can take. And that's kind of a way, a very simplified way of rewriting this. So VR for a steel beam is still, again, a reduction factor times the shape property times our stress, or the maximum stress we want to see. So VR is the reduced shear resistance. This is our material reduction factor, and for steel, it is 0.9. A, or AW, is our shape property. So look at this. This area really did almost nothing for us. All of the work is being done right here. So this is the area of our web. So AW, area of the web. So essentially, the depth of this beam times the width of the web, or W. So if you look up your steel properties or your shape properties, you will see listed D and W. So AW is just the area of this web. Now FS is the ultimate shear stress, and it varies depending on the slenderness of the web. For most of the members that exist in our steel code, that is 2/3 of Fy. They always write Fy with a capital F for shear, and it bugs me a little bit. Do you know why they write it with the capital F?
No.
I've never been able to. Normally that means you've done something with it, but there's nothing been. I'm assuming it means that you've checked your ratios, is all I can imagine, that like you've done this check. So I'll show you the check I'm talking about, and it is not a check you have to do. You would not do any of these. You are just going to use this right here. So if we have different proportions of things, so if that web was really slender compared to how long it was, we might start to look at different rules about how we calculate Fs. And so there's different kind of process to how we would do it. You guys don't need to worry about it. Most of the time, like 99% of the time, this is the actual answer that we would be using. I have definitely done ones where these are what we have to use, but you guys are not going to have to do that. So for us, Fs is 2/3 of Fy. FY is just the 350 or the 345, depending on whether we're talking about a cold rolled or a hot rolled section. So, here it all is written out as one handy sheet. This is the calculation you need to do to see if your steel beam works. This I've written out as the plastic version, but the only thing that changes between plastic and elastic is that this P becomes a Y, which really just means that you used S instead of Z. But most of the things we're going to do are going to be a class 1 or a class 2 section, which means that we're going to use MP. So if our unbraced length is really short, MR is going to be this value right here. If our unbraced length is really long, our MR is going to be this value right here. If it's somewhere in between those two, and we figure that out by using this equation right here, then MR is this equation. So there's a few things we have to check, but it's really just about saying, is the unbraced length short? Is the unbraced length long? Or is it somewhere in the middle to tell us whether we use the short unbraced length, the long unbraced length, or the somewhere in between unbraced length MR calculation. And shear is our reduction factor times the area of our web times Fs, which is 2/3 of Fy. And that's going to be all the ones you're going to be doing. That's it. That's all the information you need to be able to design your steel beams. So here, I want to show you this because it's the same thing that we had for our compressive or our compression elements. Area, or CR, was a reduction factor times Fy times a shape factor, and then we had some stuff we added in for buckling. Moment, our reduction factor times the maximum stress we want to see times a shape factor times some factors for buckling. Shear, 2/3, that's just a thing that they've added in here. Reduction factor, the maximum stress we want to see times a shape factor. Now the reason I like to write this out for you again here is because the wood industry writes all of these equations differently, but if you break it down, they are doing this exact same thing right here. So no matter what complicated equation we use, it's built off of this basic premise right here that you see. And these are things we've derived. We've developed this step by step. We started with it at its most simplistic form, which was stress times a shape factor. And then we added in our reduction factor. We talked about that the stress we really care about is the maximum stress we want it to see. Above it, it's failed. Below it, it works. So what we really care about is this maximum stress it could possibly see. And then we knew that buckling for certain types of problems can be an issue. So we added some stuff to the equation to help deal with buckling. No matter what we're talking about, this process is the same. Reduction factor, maximum stress, shape property, and maybe some other factors that are dependent on the type of load that we're talking about. And that's it. That's the basic premise. And then we want this MR to be greater than our MF. And if that works, we have a beam that works. We're going to add in deflection checks in just a few minutes as well. But let's look at, so I've shown you the very complicated way to go about this. Let's take a look at, as I've shown you in almost everything we've ever done, all of these things. We have a set of beams that exist in the world because we have this handy steel book that tells us all of these different shapes exist. And so what they've done is they've actually taken those beams and looked at a variety of different unbraced lengths and calculated out what MR and VR are at those different unbraced lengths. Remember, VR was independent of the unbraced length. So here you can see we have beam selection table for 350W steel. So we know that 350W steel is 345 for a hot rolled section. You can see down here they have a little asterisk beside anything that is a class 3 section. So you can see a W250 by 49 is a class 3 section. But not many of them have that little asterisk, which means the rest are all a class 1 or a class 2 section. So you can see FY is taken as 350 MPa for a WWF shape because it's not hot rolled. We're not doing any of those. Those are the ones where they take 3 plates and weld it together. And 345 MPa for a W shape, and our reduction factor is 0.9. These are all the things we just talked about. And they've gone through and calculated MR at different unbraced lengths for all these different elements. So you can look up what MR is. If the unbraced length is really, really, really short, they have listed here what MR is. And look, they show what LU we would switch over to these unbraced length values, where this short unbraced length calculation doesn't govern anymore. So this means it's just being governed by strength. And here's the limit of when that changes. And when it's longer than this, we have to start looking at these different unbraced lengths to find the calculation here. And so that's why some of these show dashes here. So for this one, for example, MR is 447 kilonewton meters. And that's true up to an unbraced length of almost 5 meters. So look at all of these spots here are less than 5 meters, which means all of these blank spaces doesn't mean that there's no moment resistance. It means that this is the moment resistance that we'd use. Because even though it's that for this particular element, the unbraced length is short relative to its dimensions. So that what is a short unbraced length changes depending on the shape of the element, because it's all built upon those shape properties of the element. So let's look at a beam that has an MF of 150 kilonewtons, it's a W360 by 45, an LU of 3.66 millimeters. Does this element work? So here is the 4 meter mark. Let's just take a look at 4 meters. Here is our W360 by 45, and we get 175 kilonewtons. Or 176, I believe. You guys can look this up on the tables. You guys have these tables. They're in this week's module, and they're also in the downloads section, or the available PDF section, as a different module. So you can go get them from either spot. So this would work. But let's just look at what the actual MR is at this length, just for fun. Let's calculate it out. We know that at 3.5 meters, MR is 197 kilonewton meters. At 4 meters, for an unbraced length, MR is 175 kilonewton meters. We can interpolate between these two to find out what MR is at 3.66 meters. Now, 3.66 is a little bit closer to 3.5 than it is to 4 meters. So I know if I'm going to be somewhere between 197 and 175, I should be closer to 197. I go through and I do my calculation, and MR for an unbraced length of 3.66 meters is 190 kilonewton meters. MR is greater than MF. Our beam works. We've got a beam that works. Now, they didn't ask us anything about deflection or shear, so there's maybe a bit more complication to this. And, you know, they didn't make us do the big, long, complicated equation, which I'm going to have to get you to do once or twice. But, for example, in the exam, for example, there's no place to show your work. If the question doesn't say you have to do the big, long, complicated equation, You can probably go to the beam tables and look it up. Where the beam tables might not apply, well, what if we had a different FY, for example? Like that example we had with our steel column last week, where it was a renovation of an old building. So the FY of the steel was different, so these tables didn't apply. All right, let's go through and start just digging into some calculations now. So let's look at the canopy that we were talking about last week. So we have a new canopy being built on an existing building. So last week, we did a bunch of the work already. We already figured out the dead load and the snow load. And now we can take those loads and make use of them still, because the loads on the canopy haven't changed. So for our W section, where Fy is 345 MPa, does the section work if we assume plastic behavior because it's a class 1-2 section? So the architect wants to use a W250 by 25 beam to span from column to column. So this beam right here, and we know it's a W section with 345 MPa. Does this section work if it's a class 1-2 section? Does it also work for deflection if we know that the criteria is L divided by 360 for snow loading and L divided by 240 for dead and snow together? Now they've given us two questions. One, assume there's no lateral bracing. Now, I am going to say this right now. There is lateral bracing at the top chord. So see right here, this is unlikely to be the case because look, realistically, these joists do in fact brace this top chord. There's a joist shoe, so the beam's not connected directly to the deck. This beam and our joists are connected directly to the deck. The unbraced length for all of these elements would be practically 0. So they have, however, asked us to check it, assuming there's no lateral bracing. Then they've said, assume there is lateral bracing for the top flange of the beam due to these joists, so that the unbraced length is only the distance in between these joists for this beam. So, version 1, total horseshit. It is not going to be that way, but we're going to go through the calculation. You're laughing at me. We're going to go through the calculation anyway because I want to show you the implication of there being nothing bracing the top chord of this. And then we're going to go through and look at it where it's braced at the top chord.
You just showed them your board. You let your board show.
This is because I swore, even though I promised I wouldn't swear anymore on my videos.
I know the first shit, which is...
That's what Dave and his dad say all the time. They're contagious. So we already have our loads, which is one big step in our process here. So let's make my calculation pad bigger. I have this upside down. Let's turn this upside down. Okay, hold on, bear with me. I'll stop recording and all. Okay. Now I have fixed my camera so that you will see that as the top of the page. Alright, so let's start with what the loads on the beam are. So let's start with the loads. We, last week, calculated that the dead load was 0.76 kPa and that the snow load was 1.44 kPa for ULS and 1.30 kPa for SLS. We also figured out the factored loads. We found that the worst case ULS load was an ultimate dead snow case of 1.25 times our 0.76 plus our 1.5 times our 1.44. And so we calculated this last week. I'm just kind of rewriting it out. And that for SLS, we have serviceability dead plus snow is 0.76 plus 1.3, which is 2.06. And our just snow load all by itself is 1.30 kPa for serviceability conditions. So these are the loads we're going to need to be able to design our beam. Now we know that this is a simply supported beam. So it has a free body diagram that looks something like this. We know that it's technically got a series of point loads on it, but we know that it's often assumed that those point loads are actually treated as a uniformly distributed load. We also know that there is reactions at each end and a reaction to stop it from sliding back and forth in space. These three reactions stop it from moving up and down, sliding back and forth, and the fact that there's two reactions in this direction, in the up and down direction with some distance between them, means it'll stop it from spinning in space as well. And that this length equals 6 meters. So we need to know what WF is. Well, that's based on the tributary width. Let's take a look at this beam again here. So this is the beam we're worried about. It is picking up half of all of these joists that are framed into it, or half of this dimension. So half of the canopy is coming in and loading this beam. So it looks like our tributary width is 2.5 meters, or 5 divided by 2. So now we can calculate all of our line loads, or WF equals 2.5 times 3.11. So 2.5 times 3.11 is 7.78 kilonewtons per meter. So for every meter of this beam, there's 7.78 kilonewtons on it. We're worried, we know for deflection things, we're going to want a serviceability dead snow case that we worry about. So 2.5 times our 2.06. And there'll also be our snow load case all by itself. We haven't really done anything with these yet, but we knew last term we were definitely tracking these. So 2.5 times 2.06, or 5.15 kilonewtons per meter, and 2.5 times 1.3, or 3.25 kilonewtons per meter. Now, last term, we would figure out these reactions, and then with the reactions, we would draw a partial free body diagram and figure out the internal force on this beam. We would often use a placeholder as an unknown for where on the beam we were cutting it, and we would solve using the same three equations of it not moving up and down, sliding back and forth, or spinning in space, or the sum of the forces in X must equal 0, the sum of the forces in Y must equal 0, and the sum of the moments about the Z axes must equal 0. But I also showed you last term that most of those beam load situations had already been calculated, or they were standardized enough that somebody else had done the derivations that we were just doing. In fact, this particular type of beam, a uniformly distributed load on a simply supported beam, was the most common beam type. And for that beam type, even though we've derived this manually, we've seen that other people have derived it too, and that MF equals WF L squared divided by 8, or 7.78 times 6 meters squared divided by 8 equals, so 7.78 times 6 squared divided by 8 equals 35.0 kilonewton meters. VF equals WFL divided by 2, or 7.78 times 6 divided by 2. 7.78 times 6 divided by 2 gives us 23.3 kilonewtons. Do you guys remember the compressive load on our column? Yeah, it was 23.3 kilonewtons. Or we also know that VF equals the factored reaction load at each end of this, meaning that's the load that has to go in the column because the column is what's holding up those, those beams. So this should match the compressive load in our column, which it does. Now, we also know that we have a deflection max equals L over 360 for a serviceability snow load condition, and we have a delta max equals L over 240 for a serviceability snow and dead together condition. They have also told us that this is a simply supported beam, or we know that this is a simply supported beam. Do you guys remember where these two equations are? We also have the equation for deflection for a simply supported beam. Let's see if I was smart enough to call that table up. I wasn't. Let me grab that. Beam loading diagrams. Let's open that up and put it on the page that you guys can see it. That would probably help a lot as well. All right, give me a second here. So here we have a simply supported beam. So here's our pin roller condition with a uniformly distributed load. So the exact thing I had just said. Here was our V. Our maximum V is WL divided by 2. Well, we were looking for VF, so we used WF. Our maximum moment at the center, WL squared divided by 8. Now look at this. Delta max at the center. 5 WL to the power of 4 divided by 384 EI. Well, we know W is the load, L is the length, I is the moment of inertia, and E is a property of the steel, or 200,000 MPa. So we know that the actual deflection, or deflection actual, equals 5 WL to the 4 divided by 384 EI. Now, here's where I'm going to blow your mind a little bit. I am going to, we know this is the maximum we possibly want to see, so I'm going to rearrange this because I want to find what beam works for me. I need to find what our beam needs. And one of the ways they've set up the beam charts for us, and the way we can go about this, is we often write deflection in terms of I. We want this in terms of I. So I am going to rearrange this equation. I equals 5 WL to the power of 4 divided by 384 E deflection. And so we had deflection actual, but we know that this is our limit. So we can actually end up with the maximum I, or the minimum I that we need to make this work, or the I required. So let's plug both of these in. So the I required for snow load case would be 5 WL to the power of 4, 384 E, and then our deflection, we're going to actually use our L divided by 360. So we're just taking these two things that we already know. We know that our actual deflection needs to be less than our maximum deflection. If we can get this to be right at this limit, we're probably making really good use of our steel properties. And the steel property, or the shape that we care about, shape property we care about, is I for deflection. So we're going to try to look for the one that is I is perfectly exactly what we need. Or anything less than that would be just fine as well. And then our serviceability dead snow I required would be 5 WL to the power of 4, 384 E. And then for this one, we're talking about our serviceability dead snow. So L divided by 240. I know, these look messy. All that we have done is combined the two things we already know, that we must have this less than this. The actual deflection needs to be less than the maximum allowable deflection. So we've just plugged those in to try to find the thing we don't know, or the required shape property we need. So let's plug these in. 5 times, well, W, we want the W for serviceability snow case. So the W for serviceability snow case was 3.25 kilonewtons per meter. Length. Now, let's look at our equation. E is in our equation. So the units for E is 200,000 MPa. MPa is newtons per millimeter squared, which means our length must be in millimeters then. So it's not 6 meters, it's 6,000 millimeters. To the power of 4 divided by 384 times 200,000 MPa times 6,000 divided by 360. I can tell you that I have plugged this equation in, changing that number, and that number, and that number, easily 1,000 times, probably more than that. I have plugged this equation into my calculator. Let's calculate this out and see what number we get. All right, we have 5 times 3.25 times 6,000 to the power of 4 divided by, and I'm going to put it in brackets, 384 times 200,000 times, and then again in brackets, 6,000 divided by 360. Now I've got to make sure I end both of my brackets. And look at this. I get 16,453,125 millimeters to the 4. Remember, I is in millimeters to the 4. Well, that's a pain in the butt to write out. I'm going to write it in the times 10 to the 6. So 3 and 3. I'm just rewriting it a different way. 16.45 times 10 to the 6 millimeters to the 4th. So I need at least an I of 16.45 times 10 to the 6 millimeters to the 4th. But I have always stressed that there are two different deflection criteria, and the values change, but so does the load. So it is not always easily apparent which one governs. So let's write out this limit as well. 5 times W, but it's the W for dead and snow serviceability case, or 5.15. Our length stays the same. 384 times 200,000 MPa. Our length again stays the same, but our deflection criteria is different. So you can imagine that knowing the outcome of which one of these is going to be bigger is not always obvious. If we have a situation where we have heavy dead loads, well, this could end up being the one that governs. If we have light snow loads, maybe this one governs, but it's not obvious because we're dividing out by different criteria here. So let's plug this in. 5 times 5.15 times 6,000 to the power of 4 divided by, and I'm going to put this in my brackets, 384 times 200,000 MPa times, now brackets to put in my deflection criteria, or 6,000 divided by 240, end both of my brackets. I get 17,381,250, or 17.38 times 10 to the 6 millimeters to the 4th. So now we actually know which deflection criteria governs. We need an I required. So this is an I required and this is an I required. Well, if it was just snow, we need that I. But if it was dead and snow, we need this I. So this is the ultimate I required. So for this beam to work, we need an MR greater than MF, which was 35.0 kilonewton meters. We need a VR greater than VF, which we calculated to be 23.3 kilonewtons, and we need an I actual greater than our I required, which is 17.38 times 10 to the 6 millimeters to the 4th. So if we can find a beam, we need a beam that has these three things to be truths. We need an MR greater than 35 kilonewton meters. We need a VR greater than 23.3. And we need a member that has an I, or a moment of inertia, greater than 17.38 times 10 to the 6 millimeters to the 4th. If we can find a beam that has all of these things, we're going to have a beam that works. So now we can move on to figuring out what we know. They've given us a beam to check. So we can start looking up those things or figuring those things out. Now again, I always like to write out what we know. What we know. And I usually start with my steel. Well, we know Fy, because it's a hot rolled section, is 345 MPa. E is something we know, 200,000 MPa. It's a steel beam. That's something we know as a truth. Reduction factor, I've told you guys for steel, It's 0.9. And G, we know, has some relationship to E, but I've told you that it is 77,000 MPa. Well, let's figure out what we know about the member. They have given us a member to check, a W250 by 25. And they've asked us to check this two different ways. They've asked us to check this with two different LUs. Well, there's a bunch of things that we can look up about this member. Let's take a look here. Let's take a look at our steel sections here, eventually. All right, here we are with, let's go to the next page, a W250 by 25. So here's the member we're concerned about. And up here, look at this. We've got area. We've got IX, which we know we might need for the deflection. SX and ZX, well, they told us it was a plastic section, so ZX seems like the thing we're going to need. And we know for lateral torsional buckling, they're talking about it bending or deforming or buckling in the weak axes, so we'd want IY. And then there was a few other constants that I told you we'd have to look up just to mess with you. Okay, not just to mess with you, because they help us out just a tiny little bit. But we've got a torsional constant and a warping constant of J and CW. Look at these numbers. So whatever this number is, it's actually times 10 to the 9 millimeters to the 6. Just an absolutely ridiculous kind of number, but there are constants that are going to help us out. Constants for these shapes. So for our W220 by 25, it looks like we could look up all of these values. Of course, I've made it a white box. There we go. So we can pull out all of those things that we know based on the shape. So looking at that table, we know that the area is 3,230 millimeters squared. IX, we know, is going to help us when we're talking about deflection, is 34.2 times 10 to the 6th millimeters to the 4th. IY, which we know we tend to talk about because of our weak axis buckling problem, is 1.49 times 10 to the 6th millimeters to the 4th. They gave us two different LUs to worry about. The first one was assume nothing is bracing the top chord, or a full unbraced top chord. Not real. I want to stress this. It is not real. It would be braced by something there because there's joists framed into the side of it, and if it was a beam with deck on it, the deck would be bracing it. The other thing they told us was that it could be braced by the joists. Well, if we look at the joist spacing, there's a joist every meter. That seems like we've talked about before how usually for joists supporting metal deck, they're every 2 meters, but we don't know what governed the design here. So the unbraced length in the second version they've asked us to look at is 1 meter, because there's a joist every meter along the length of that beam. There's a few more constants we can look up. J is 65.2 times 10 to the 3 millimeters to the 4th. And CW, which is the kooky number I told you about, is 23.0 times 10 to the 9 millimeters to the 6th. So an absolutely gigantic number. So we have a few other things that we need to know. There's some more shape properties. We know that for shear, we only care about the area of the web, which is D. And if we look up the actual depth of a W250 by 25, it is 257 millimeters. And if we look up the width of that web, or how thick that web is, it is 6.1 millimeters. And they said that it was a plastic bending section, or a class 1 or a class 2 section. So we can look up ZX is 307 times 10 to the 3 millimeters cubed. So everything except these two numbers we looked up from the steel shape properties, or the steel sections. So these are the two things that came from the question. So now we need to calculate the moment resistance. Let's do number 1. So moment resistance for a class 1, class 2 section. So if it's class 1, class 2, that means we get to use the plastic section, which means we're using MP for everything instead of MY. So there's a few steps to this question. The very first thing they ask us is MU greater than 0.67 MP. Is this the case? So it looks like we need to calculate MU and we need to calculate MP. MP, we know, is FY ZX. Well, let's see. Are these things we already know? FY, we know, is 345 MPa. And ZX, we looked up from the member chart, where it told us the shape properties and the different properties of that member. So we know that this is 345 times 307 times 10 to the 3 millimeters to the 3rd. We plug this in, so we have 345 times our 307 times 10 to the 3. So we have, let's look at this, 105,915,000. And that is Newton millimeters. Well, I've told you before that we hate talking about moment and Newton millimeters. We need to when we're doing the calculations, because all of our data comes to us in millimeters and newtons. So we need to convert this into kilonewton meters. So this is the same as divide by 1,000 and divide by 1,000, or 105.9 kilonewton meters. So now we know what MP is. They've also asked, so we also need to find out what MU is. MU. What a nasty, ugly equation this is. All right, let's write it out and we'll do the calculation in steps. So we have W2 pi divided by our unbraced length times the square root of E IY G J plus pi E divided by L, which is our unbraced length. That is inside a bracket that is squared. times IYCW. All right, losing track of placeholders in this is going to be your biggest difficulty. We're going to go through this with this one and the next question, so you're going to see that plugging things into your calculator is a bit of a skill. Maybe you want to break it into stages so that you don't lose track of these. Now just remember that L is really LU. It's super important to remember that in this equation, they're saying that L is the unbraced length. Well, for this version, our LU is the 6 meters. Remember, that was what we had 2 different ways we needed to calculate this. So this is the version where our unbraced length is the full length of this beam. So let's plug this in very slowly and very carefully. It makes for a very messy thing to write out. In fact, I'm going to have to end up writing it on 2 lines, unless maybe I start all the way over here. So this is MU equals. Now W2, I told you was going to be 1 for you guys, and we know that pi is 3.14. Our LU is 6,000. All of this is times the square root of all kinds of stuff. E is 200,000 MPa times IY, which is 1.49 times 10 to the 6, times G, which is 77,000 MPa, times J, which is another shape property, J, which is 65.2 times 10 to the 3. Plus, there's still more, 3.14 times 200,000 MPa divided by 6,000 squared times our IY, which is our weak axis bending, of 1.49 times 10 to the 6th, times CW, which is our 23 times 10 to the 9. All right. Look at this. We have to plug this into our calculator. All right. I'm going to admit that most of you will probably have a hard time plugging this in, and this is probably where you're going to go wrong. So maybe plug it in a few different ways. Track yourself and check yourself. If you guys want to communicate with each other on this step throughout your assignment, I have no problem with that. Assignments are supposed to be talked about and worked through together. What I don't want is you to call each other up and say, yo, here's the answer. I mean, you could totally do that. How am I going to mark you on that? But you're going to be the one to suffer for that. So I suggest you try to go through it on your own and practice plugging it into your calculator again and again. But you might find it helpful to talk it through with some of your colleagues in the class. All right, I am going to go through it, kind of breaking it into stages of plugging this in. I'll work out this, and I'll work out this, and I'll work out this. Just in our first 3 steps, just so we can kind of track this with each other. If you're a pro with a calculator, go through and plug this in all at once. I have no problem with it. Maybe try doing it by stages so you can track me, and then try plugging it in all at once to see how it goes for you. All right. 1 times 3.14 divided by 6,000. I am going to write everything using scientific notation. So this is a very small number that we have here. 1, 2, 3, 4 places over. So we have 5.23 times 10 to the minus 4. I meant to do it in the color of pen that we were talking about. Times the square root of, so let's plug in the green one now, or 200,000 times 1.49 times 10 to the 6 times 77,000 times 65.2 times 10 to the 3. All right, look at this number. It is to the 21 times 10 to the 21. So we have 1.496 times 10 to the 21. That was calculating out that portion of it. And now we're going to plug in the purple one. Or let's make our brackets. 3.14 times 200,000 divided by 6,000 squared times 1.49 times 10 to the 6 times 23 times 10 to the 9th. So for this one, we've got 3.754 times 10 to the 20. Or, so this is a plus here. 3.754 times 10 to the 20. So you could break this down and do it in a few more steps if you felt like it. I'm going to go ahead and plug this into my calculator now. So I've got 5.24 times 10 to the minus 4 times the square root of two things added together. So I'm going to do my bracket so that I keep my order of operations correct. 1.496 times 10 to the 21 plus 3.754 times 10 to the 20. And my bracket, so it's all under my square root. And I end up with 22,624,813. Or this equals 22.62 times 10 to the 6 Newton millimeters. I know I like to talk about things in kilonewton meters at this stage, so it is 22.6 kilonewton meters. So the very first thing they asked us in this equation is mu greater than 0.67 MP. So let's see. Mu equals 22.6, and we want to know if it is greater than 0.67 times MP, which was our 105.9. So 0.67 times 105.9 equals 70.95. It is not greater than so this was 0.67 MP, just so that we can keep track of it. Mu was not greater than that. So if we go back to our original equations, let's just go back and take a look at what those equations look like. Oh, I actually want this. Let's go back and look at this equation. If mu is greater than this, do all of this. If it's not, mr equals the reduction factor times mu. So it looks like we don't have to do that big, crazy equation for this beam. For us, MR equals our reduction factor times MU. So we can check this right away. 0.9 times MU, which we just calculated to be 22.6, or 0.9 times 22.6 is 20.3 kilonewton meters. Let's just for our own sanity go check that in the steel beam tables. So here was that PDF that we had been looking at. And look at this, our this is just our shape properties. Let's look at a steel beam table. We're looking at our W250 by 25, which is right here. Let's make this color red right now, and no fill. So we're talking about that line of information. And we're talking about an unbraced length of 6 meters. Well, look at this, 20.4. The beam tables gave an MR for an LU of 6 meters. So the beam table gave an MR for an LU of 6 meters of 20.4 kilonewton meters. We didn't do anything wrong in our calculation for this 0.1. This was just about rounding throughout these steps. Maybe if we had kept a few more significant figures at each of these steps, we would have ended up with 20.4 here as well. So don't worry about that. I am comfortable with it being that much off. It is very, very close, but what's nice is you do have the ability to go back and check here. If we were using a steel that had a different FY, we might not have been able to do that. So here's the thing. Our question was, is MR greater than MF? We need all of those things to be true. MR equals 20.3 kilonewton meters is not greater than MF, which was 35 kilonewton meters. Does not work. So it's always nice to kind of write big numbers on here that reminds us that this one did not work. So nobody comes along and thinks, great, here's our answer. We like to put big, bold letters. Back in the day before we had design software, every project I did had a big binder, and every beam had its own sheet of paper where we went through, and every page had these loads figured out and this drawing done on it, all of these steps worked out, and then at the end, we would have a little table like this that said if all of these things worked, and we'd put check marks beside it. And maybe we'd write a little table so we could put a few options so that there were selections in what might work. So there was 2 things we needed to check. We also needed to check with all of this information, but with LU of 1 meter, to see if this whole idea of bracing the top chord really makes that much of a difference. So this is a long lecture. I do apologize. This is probably the longest lecture of all of the classes that we do. I've very rarely taken you to 3 hours. If we push a few minutes past it, I'm very, very sorry. Dave, if I am not done at 4:25, I know you're under like the most insane deadline. but could you go watch the kids for a few minutes until I finish up? I'm so sorry to ask it of you, but I need to get this posted to them today. And it's the critical lecture.
Yeah.
Okay. So we're going to do the second version of it. Top chord braced. So LU is 1 meter. Otherwise, nothing else in this problem has changed. Absolutely nothing else. It's essentially like we now have 5 Daves standing there with their finger holding the top chord of this beam, the same way Dave did with his finger on my foam block. So it's the exact same concept. It does not take much load to brace the top chord of this, but it's a very important part of getting our beams to work. Because let's see what happens with this very small assumption that is in fact true. If the member is there, it is going to brace the top chord. So the very first thing they ask us to check is mu greater than 0.67 MP. Well, do you guys remember that MP is irrelevant of what the length is? It didn't matter what the length was for calculating MP because it was just about strength. Let's come back and even look at our MP equation. Look, Fy times Zx. There's nothing to do with length in there, and the only thing that is different in this version of the calculation is that LU has changed. So MP is going to stay the same, and 0.67 times MP is going to stay the same. So is mu greater than 0.67 times 105.9, or what we calculated out last time to be 70.95 kilonewton meters. If mu is greater than this, we can go on to the rest of the equation. But we have a new mu because mu is dependent on the unbraced length. That is the key here. What is the critical buckling moment? And that is dependent on how long our unbraced length is. So mu, let's take a deep breath. We're going to write it out again, is W2 pi divided by L, which is our unbraced length, that's right here, times the square root of E IY G J plus pi E divided by L, those are in a bracket and squared, times IY CW. We know that this is about what type of beam it is and what the moments are at the end, but we've got a beam with 0 moment at the end, so we get to use 1. This is a constant in the world. This is our unbraced length. That's about steel, that's about the shape, that's about steel, that's about the shape. Constant in the world, that's about steel. This is our critical thing that we're worried about, LU. That's about the shape, and that's about the shape. So as much as this is a big, ugly, scary equation, there's not much in it when we break down that we don't know. Most of it is just stuff we look up about that particular shape. So let's plug this all in, and we'll go through that very careful process of plugging the equations into the calculator again. So our W2 is 1 times 3.14. Oh, look at that. I did it. I promised myself I wouldn't do it. I did find, hidden down here, a whiteout strip, if I can get it to work. It's really old. No, I am not getting that to work. So, our unbraced length is 1 meter now, times the square root of E is about the steel, and is 200,000 MPa. IY doesn't change, and is 1.49 times 10 to the 6. G is about the steel, and is 77,000 MPa. And J is a constant. It's the torsional constant. Again, it's about a shape property. And it is 65.2 times 10 to the 3. Plus 3.14 times 200,000 MPa divided by our 1 meter, and that's squared, times our IY, which we've already used over here, times our CW, which is 23 times 10 to the 9. So it's a big, nasty equation again, but the only thing that is different from this version and this version is 6,000 here and 1,000 here. That's the only thing that has changed. So let's plug this into our calculator the same way we did last time, and I'll break this down for us just to help us practice plugging these into calculators and kind of keeping track of these things. And I've just kind of given them a color highlight here for us. One times 3.14 divided by 1,000. We have 3.14 times 10 to the minus 3. Last time we had something to the minus 4, so it's a magnitude, an order of magnitude different there. Times the square root of, let's just help ourselves keep track here. We're going to plug in everything underlined in green here. 200,000 times 1.49 times 10 to the 6th times 77,000 times 65.2 times 10 to the 3, and we get 1.496 times 10 to the 21. Well, that's the same thing we plugged in that we got last time, because nothing in this part of the equation changed. That makes sense. Over here, we do have something different. So this is going to come out with a different number. We have 3.14 times 200,000 divided by 1,000. All of that is squared, times 1.49 times 10 to the 6 times 23 times 10 to the 9 equals, let's make sure I've plugged this in correctly. All right, we get plus 1.3516 times 10 to the 22. Now here's the big thing. This was times 10 to the 20 last time. That is 2 orders of magnitude different. That is like comparing 100 and 1. Very different things. We are that much bigger. So let's see what the implications of that are. Let's see what mu equals. We have 3.14 times 10 to the minus 3 times the square root of, and I'm going to bracket this because it's addition, 1.496 times 10 to the 21 plus 1.3516 times 10 to the 22. End my bracket. And we get 384 384.7 times 10 to the 6 Newton millimeters. We like to write things in kilonewton meters now, or 384.7 kilonewton meters. So remember, this is our critical buckling length. If this is really, really short, it's hard to get it to buckle. It takes a lot of moment to get it to buckle. When it was long, it takes much less moment to make it buckle sideways. So is mu greater than, well, let's see, mu equals 384.7. Is it greater than 0.67 MP, which equaled 70.95? Yes. So that means we have to use that Steele equation. So remember, if this wasn't true, mu became our moment resistance. We just had to apply our reduction factor. If not, we had to figure out what the range was. But there was also an upper bound on that. So therefore, Mr equals 1.15 times our reduction factor times MP, which is times 1 minus our 0.28 MP divided by mu. Remember, this is very much like our lambda portion of our Steele equation. But they also said that this needed to be less than by, or reduction factor, MP. So let's take a look at what all of these values are. Let's plug in this equation right here. So 1.15 times 0.9 times MP, which we've found. MP was 105.9. This was 0.67 times MP, but MP was 105.9 times 1 minus 0.28 times MP, which is 105.9, divided by our mu. And mu was 384.7. And this needs to be less than 0.9 times MP, which was 105.9. So here we have 1.15 times 0.9 times 105.9 times bracket 1 minus 0.28 times 105.9 divided by 384.7 end bracket. We get 101.2 kilonewton meters, but it must be less than 0.9 times 105.9. 105.9 times 0.9 is 95.31. So that means this isn't our answer. This is Mr equals 95.31 kilonewton meters. Now, so what this is saying is that this is so short, it's being governed entirely by strength. This one, the unbraced length, was so long, it was being governed entirely by weak axis buckling of the top cord. If this had been less than this value would have governed, and it would have been saying that it was some combination between those. It wasn't that short, but it wasn't that long, and it was somewhere in between, and then this equation would have governed. So now we've gone through calculating all the different ways the beam could be governed by moment, and 2 of them have been our final answer. So we have an MR. This isn't the end of what they asked us, though. We need to check what VR is as well. VR is our reduction factor times AW times FS. We know that FS equals 0.66 times Fy. Well, we know that AW is our depth times the thickness of our web. So it looks like we have everything we need to plug into this equation. VR equals 0.9 times D times W. Well, D was 257 and the thickness of our web was 6.1. And then FS, 0.66 times Fy, and for a hot rolled section, that is 345. We can plug all of this into our calculator, and we get 0.9 times 257 times 6.1 times 0.66 times 345, and we get 321,268. Sorry, that's in newtons. We like everything in kilonewtons by the time we get to the end, or 321.3 kilonewtons. Let's just double check these things in our steel beam tables. So it's the same steel beam. Look at this. For an LU that is less than 1.33 meters, MR is 95.3. Well, we calculated 95.3. And VR is 321. We calculated 321. And look at this. IX is 34.2. We've already pulled that off somewhere. Let's take a look here. Yeah, IX, 34.2 times 10 to the 6 millimeters to the 4th. So it looks like we may be able to figure out if this beam works or not. So we have MF equals 35 kilonewton meters. VF equals 23.3 kilonewtons. I required was, in the example I have posted for you guys, I only did one of the deflection checks, but we're doing both of them. 17.38 times 10 to the 6 millimeters to the 4th. We need all of these things to be less than all of these things. Let's take a look. We have a W 250 by 25 with an LU of 1 meter, and we calculated that MR equaled 95.3 kilonewton meters. We calculated that VR equaled 321.3 kilonewtons, and we've looked up the I actual, we looked that up, is 34.2 times 10 to the 6 millimeters to the 4th. Well, let's see. MF is less than VR, is less than MR. VF is less than VR. I required is less than I actual. So yes, yes, yes. Our beam works. So we have finally an answer for a steel beam that works for us. So that's huge. We now are able to manually calculate these things all the way through. I want to show you some cool little things about this beam chart that I showed you right here. So here are all the beams. They show you VR, IX, and MR. That's super duper handy for so many things. They also show us B, which is the width of our beam. Sometimes there are certain types of projects that might have limits. Maybe we need to fit this beam in a wall. So they might say, don't let B be greater than 110. So we need to keep with something very narrow. Or maybe we're supporting something specific on top. For example, hollow core has a clause that all of your steel beams that are picking up hollow core on both sides need to have a B of greater than 165 millimeters. So look, our W250 by 25, even if it was strong enough and stiff enough, wouldn't have worked because it couldn't have had the width that we needed. So sometimes there can be other criteria on this. And remember, cheapest is what rules all, and this line right here tells us the relative weight. So if you've got two beams that VR works, MR works, and the I required works, you're then going to look at the one that is the cheapest, which means weighs the least. After that, then you might worry about which one is the deepest. Sometimes you might have criteria on a beam of, I don't care that it's the heavier section, but I need one that I don't bonk my head on every time I go down the stairs. So they might put a depth requirement on it, that you cannot be deeper than this specific depth. And so in those ones, again, you don't have the exact answer written right here, but you're pretty darn close. Maybe then you need to pick one that's pretty close and then go look up what the actual depth is. But from these charts, you can figure out some pretty great stuff about which beam is going to be the right one for your project. Again, this is just formalizing all of these calculations we did right here. Every single one of these spots is one of these pages of calculations. They've just done it for all of these beams for all of these lengths. And so we will do a couple of them. You'll do one or two in the assignment, but that's just to get you familiar with the process. Again, if I don't tell you you have to do the calculation, I'm going to suggest that you look it up in the beam table. If you do have to do the calculation and there is a beam available in the beam table for you, maybe double check it and cross-reference it with yourself. Okay, let's just, here that is all worked out. Here are those values that we pulled out. So the next thing I wanted to ask, is there a better answer? Let's come back to this. We're using a W250 by 25 here, but we know that weight governs all. So we need something with a VR that works for us and an I required that works for us and an MR that works for us, but is there one that also weighs less? Well, let's start with down here at the lightest weight. This is our MR category. All of these, we have an LU of a meter. All of these are greater than a meter. So they're all governed by just strength. So let's take a look. Well, we need 35 kilonewton meters. So that doesn't work. That doesn't work. That looks like it could work. Oh, but look. The I isn't enough. We also need an I required of 17.38. This works, but I doesn't. This works, but I doesn't. Ooh. MR of 55.6. The right unbraced length, we needed it to be at least a meter. We have a shear capacity that works. and an I greater than the 17.4 we need. So look at this, it's a 250 by 18. It looks like we could use a lighter section here. It's got the funny little asterisks on it here. Let's take a look. It's a class 3 section, but these are already the calculated out tables. They used MY instead of MP to calculate these. If you want, feel free to take the properties of this W250 by 18 and do what we did here, and instead of using MP, use MY, which is based on SX instead of ZX, and see if you can replicate these answers. Again, this isn't something you have to do, but if you're a person who likes to do more problem solving, you can check some of these. In fact, if you're looking for example problems, you have a gazillion of them right here on this page. Pick one of these unbraced lengths, pick one of these members, and see if you can calculate the corresponding MR. Okay, we are very short on time here, but I have worked out 2 examples for looking things up on the beam tables for you. So these are worked out examples. I'm not going to go through them because I think there's enough information that I've gone through for you, and these are references. It's not the fully worked out problems, but you can see we have 1, 2, 3, 4, 5 beams that are all the same, and we have 2 beams that are different. These beams are braced by these beams, and it looks like these 2 BO3s have the deck sitting directly on them. The unbraced length for 2 BO3, 0. They are fully braced. 2 BO4, maybe their unbraced length is 0. Maybe it's 2 meters. In fact, I'm saying that because I can't remember what I actually did for you guys. Let's see here. Tributary width. LMAF was 525.6. Oh, well look, so it's irrelevant. The LU was greater than 2 meters anyway. So go through these. You don't have to do the big calculation, but you can calculate MF and VF and the I required. And then you can go through and find if your MR and your VR works out for all of these. I'm feeling like I wrote something down funny there for you guys, but let me just... Yeah, I wrote this backwards here, guys, so I'm going to fix this. Don't read this from my lecture. Read this. This is supposed to be flipped here. Your I required should be less than your I actual. And then you can, or sorry, your I required should be right here, and your I actual will be over here. I'm going to update that for you and put that into the slideshow for you, so you'll be able to look at it there. And so you can go through and try these. The reference information is all right here to give you the opportunity to practice on these. And then here is the written out information on the plan. So the forever tips. Remember that a beam tends to buckle sideways on the top chord if they aren't restrained. Elements could have local buckling. And we list if they're prone to it or not right in the classification of the beam. Beam design looks at bending, shear, and deflection, and lateral torsional buckling and slenderness are related. Studying, you should know how to identify a class 1 or class 2 from a class 3 or class 4. It'll be right there in the chart. It says it right there in the beam tables. You should know what the interaction diagram of stress and lateral torsional buckling looks like for beams. Again, great type of exam question for labeling things. You should know how to calculate MR for beams. You should know how to calculate VR. You should know how to calculate I required. and you should know how to look up MR, VR, and I for available beams. You want to pick the cheapest, lightest beam that works. After that, maybe worry about the shallowest. And you should know how to identify if the beam works. And that's by saying that MR is greater than MF, VR is greater than VF, and the I actual is greater than the I required. And if all of that works, then you can check it off. Again, I like seeing the nice little layout here of that, saying that. Okay, this was a big week. Next week is your spring break, unless I've got everything wrong, but I'm pretty sure next week is your spring break. So you get a week to breathe, and then we're going to come back and talk about a new material. Everything we're going to do with wood is everything we just did with steel. So there's no new concepts except for the fact that the material properties change. And wood is a little bit interesting because it's organic. But other than that, the process is going to be very similar. We have to add some stuff into the process because wood is organic. We grow it. We don't make it in a plant and have it highly refined. But we have systems in place that take care of that. So enjoy your week, and I will see you guys in 2 weeks.